Hello there guys, welcome back to another epic maths video. In this video we're taking our second look at the Gambler's Ruin sequence of questions in stochastic processes, simple random walks, etc. So let's just remind ourselves what we've been looking at. So let xi be a sequence of random variables taking values +1 with probability p and -1 with probability q, which is also 1 minus p. Let k be a number between 0 and m, where k and m are natural numbers, and let Sn be k plus the sum of all of those xi's up to n, and let t be a stopping time such that we take the smallest n such that Sn is either 0 or m. So if you've not seen my previous video on Gambler's Ruin, go and check that out. I'll leave the link in the description. Super important to watch it because we're going to build on this. In the last video, what we did is we found that the probability of starting at some point k and then stopping at m is given by either this expression or this expression, depending on what p is. We solved a recurrence relation or a difference equation, and we ended up getting this. So if you start with k pounds or k dollars, and you play the game, you play the simple random walk, you gamble, maybe you win your first one, then you lose the second, and then you lose again, and then you win, and then you win, and then you lose, and then you win and win and win and win, maybe. That could be one situation. Well, the probability that you start at k and eventually you get to m before you get to 0 is either k over m in the case of a simple symmetric random walk, and this expression here in the case of an asymmetric simple random walk. That's what we did in the last video. Okay, recap over. In this video, what we want to do is find the expected value of t. So in other words, how many games, how many iterations do we have to actually play before either the gambler loses all their money or wins the m pounds that they said, okay, if I win this, I'll stop. How many games on average will it take? Of course, it's going to depend on what p is, it's going to depend on what k is, and it's going to depend on what m is. And in this video, we're going to find an expression for it. Let's go. Okay guys, so before we start doing calculations, what we're going to do is we're going to implicitly assume that the expected value of t is a finite number. But we should make some sort of argument as to why it is finite, because maybe this is infinity. And if it's infinity, then anything that we do involving the expected value of t is just going to be a bunch of BS, basically. So we should come up with some argument as to why this is definitely not infinity. And I'm just going to do this really quickly, because if you want to do this properly, you need measure theory, you need some high-level probability stuff that we're not going to tackle. So I'm just going to make an intuitive argument about disjoint blocks here. So if we split the simple random walk into disjoint blocks of length m, if I start at k, then one possibility for the gambler's wealth is that they could just win every single game and go like that. Their wealth just does that. Another possibility is they just lose every single game and their wealth does this, okay? So each of these events has a certain probability of happening. Let's say that it doesn't happen, okay, because it probably won't. Maybe they lose, they win, they lose, they win, they lose, they win, for example, and then you get to m. Now, because these blocks are totally disjoint from each other, the probability that the same thing happens is it's the same, right? So the gambler could either just again win everything here and their wealth goes like this, or they just lose everything and their wealth goes like this. And in all likelihood, it won't happen, but it could. Let's say they win, they win, they win, they win, they win, and then they lose. We can then look at the same thing again, disjoint blocks. The probability is the same, whatever that might be. They could win everything or they could lose everything. One of these things could happen. And it happens again, and it happens again. And basically the logic as to why this is definitely not infinity is you can look at this and you can make a comparison to a geometric distribution, because you've kind of got the probability of this, either this outcome or this outcome happening is some number. The probability of either, this outcome or this outcome happening is the same number. The probability of either this or this is the same, or at least you can bound it by the same number. And so what you can say, because there are other ways for the gambler to either hit 0 or hit M, right? For example, you could have loses the first and then wins all of them. That could still work. So because of this, the likelihood of getting a, what I might call success, which is the game ends, is actually higher than in a geometric distribution, okay? And because of that, because a geometric distribution has a finite mean, finite expected value, this must have a finite expected value as well. So don't worry too much about whether that makes 100% sense to you or not, because it's not formal. And the best way of doing it is by looking at measure theory. And if you know about measure theory, you might be thinking about something like the dominated convergence theorem, which is basically what the argument that I'm making kind of is. We're bounding it by another random variable that has a finite mean. So don't worry about this too much, but it's super important because you're about to see it in a second. We're going to assume that this is finite, and we have to explain why it is finite. It's really important. Okay, let's go. Okay, so let's let E sub k of t be the expected duration of the game if you start from k. That's just some notation. Then what I can do is I can take a weighted average of this to rewrite it. It's kind of like the partition theorem. So I can rewrite the expected value of t, given that I've started at k, as the expected value of t given that x1 equals 1 when I started from k times the probability of this happening, the probability that x1 is actually equal to 1, plus the expected value of t given that x1 equals minus 1 starting from k times the probability that x1 is equal to minus 1. If you don't know about this formula, don't worry too much about it, but this is basically a weighted average, okay? So it's the expectation of the number of games that's played given that we've started from k, and also given that the first game is a win times the probability of it happening. It's a weighted average, and then same thing with the first being a loss. It's very similar to the setup of the last one, okay? And then what we can do is we can replace this with a p. This is just p, isn't it? And then this is just q, okay? And basically we have got another recurrence relation, because what we can do is we can say this is still the expected value of t, and then this is equal to, so this is, you've started from k, how many games does it take in order to eventually stop, given that the first one is a success, you win your first game. I can actually rewrite this in a clever way as the expected value of just starting from k plus 1, okay, because I've just gone up by 1, but since you've already had to, you've already had to win a game, and here you haven't, I also need to add 1 to it, okay? And then there's a p here. This is the first bit. So I've added 1. This is something that confuses a lot of people. Again, I'm just going to say it one more time because I don't want anyone to get lost at this stage. I'm starting at k, and this represents the average number of games that need to be played, given that the first one was a success. So I've gone up. The first game is a success, so I've gone up. And what I really want to do is rewrite it with a subscript of k plus 1. So I can do that. I can say, well, it's the same as the average number of games that need to be played, given that I've started from 1 higher. So that's if I've started from k plus 1. But obviously, if I start from k plus 1, it's not exactly the same because I'm 1 step behind from here. So it's the same as starting from k plus 1, but I've also got to move 1 step across. So I'm here again, if that sort of makes sense. So that's why there's a plus 1 there. And then it's the same thing with this. So this is plus the expected value starting, this time I'm starting at k minus 1. So I can put a minus 1 down here. And then that is also going to have a plus 1 in front of it for the same reason, because yes, I'm starting at k minus 1, but I've also got to go 1 because I've already spent a step. I've spent a gamble, so I have to also include that plus 1. And then there's still a q here as well. And the reason I've done this is because now this is a cold, hard recurrence relation because the k's are all in the same spot. So I can rewrite it, use some slightly different notation, and I've got a recurrence relation. So I'm going to let the expected value starting at k of t just be tk. It's a little bit easier to use that notation. And then what we can do here is we can rewrite this as tk equals tk plus 1 times p plus tk minus 1 plus 1 times q. Okay, and we've got this here, and we can rewrite this at the top, and then we can start doing some rearranging. One thing I'm going to mention is I am going to do this question using the simple symmetric random walk, because this is really, really complicated and it takes a long time. But I will put an overlay on the screen right now if you want to see the solution to this recurrence relation or difference equation with P and Q left how they are. So I'm going to do the working out for a simple symmetric random walk, but right now on the screen, you'll be seeing the non-symmetric solution. Okay, so I've just rewritten the recurrence relation and I've expanded it out. And as I've said, we're going to do the simple symmetric version. So I can replace the P and the Q with 0.5 or 1/2 and rewrite. So I've done that and I've multiplied it by 2 just to get rid of the fractions. And let's get it in the right form to solve the recurrence relation. So it's tk plus 1 minus 2 tk plus tk minus 1 equals minus 2. And now what we can do is we can solve it. So as always, we can guess, we can find the complementary solution, the complementary function here. We can guess tk might be some number to the power of k. Okay, so I'll say r to the power of k. That's a guess. And then what we can do is we can plug in. So we've got r to the power of k plus 1 minus 2r to the k plus r to the k minus 1. And remember, when we do this, we're solving the homogeneous version. So I'm going to ignore the minus 2 for a second, and I'm going to set it equal to 0. I can then divide everything by r to the k, and I can times everything by r to get r squared minus 2r plus 1 equals 0. And hopefully it's clear to see that that means that r is the number 1. What this means as far as the solution goes is that we're going to have tk, and remember, because it is a second order recurrence relation, there will be 2 linearly independent solutions. So we've got a constant, so normally it's a times r to the k plus b times the other r to the k. They're both the number 1, so we're going to have a plus b k, and then times 1 to the k, so just nothing. So that's what the solution is going to be. It's just going to be a plus bk, and then we need to include the minus 2. So because minus 2 is a constant, we might assume that the particular solution will be a constant as well, but we can't because there's already a constant in the complementary function. There's also a linear function as well, so we have to assume that the particular solution is a quadratic, or at least it's just a something times k squared. So I've just rewritten, and I'm going to assume the particular solution is ck squared. I'm going to plug that in and work out what c is equal to. So I've done the algebra, and I can see that a lot of stuff is going to cancel out. So I've got a ck squared and a ck squared that cancels out with the minus 2ck squared. I've also got a 2ck and a minus 2ck that are going to cancel, and then I've got c and c. So I think I've got 2c equals minus 2, which means that c is minus 1. So my particular solution is minus k squared. Now I just need to work out what a and b are. Okay guys, so now we just need to find a and b in a plus bk for the complementary. Let's also think about some boundary conditions, because we've not spoke about those yet, and you need boundary conditions to find a and b. So let's just notice something. T0 is going to be something, and Tm is going to be something. Remember that these just mean the expected duration of the game, given that you started at 0 and that you started at m, respectively. If you start at 0, and remember, t is the stopping time that says if you hit 0 or m, you instantly finish the game. If you start at 0, the expected duration of the game is 0. And if you start at m, same logic, right? If you walk into a casino and you say, I'm going to leave the casino as soon as I have M pounds, if you walk in with M pounds, you're leaving, right? So it's 0. The expected duration is 0 for both of them. So now what we can do is we can say, okay, well, it looks like TK is a plus bk minus k squared. Let's plug stuff in. So let's plug in 0. So 0 is a plus 0 minus 0. So a is 0. Nice. Let's plug in m. So 0 is, well, a is already 0. So it's b times m minus m squared. Okay, that's just me plugging in m. And then we can just work out what b is using this. So 0 is equal to m times b minus m. So that means that either m is 0, which it's not, we said it's greater than 0, or b minus m is 0. So that means that b is actually just m, okay? So kind of final solution here, tk is going to be a, which is 0, plus m times k, so m times k minus k squared. Okay, and this is the expected, this is the answer. So just to be clear, the expected duration of the game, if you start at k of t, yes, is m, or we could factor it, we could have k times m minus k, okay? That is the answer. And again, that's for a simple symmetric random walk. That is when p is 0.5. Now, one more thing I'll leave you with is I'm going to give you some numerical examples of this. So, for example, if k is 20 and m is 100, then the expected value of t is, of course, just 20 times 80, which is 1,600. Now, I don't know if that's surprising to you, but to be honest, and again, this is a symmetrical random walk, to be honest, it surprises me how big of a number it is. So if you walk into a casino with £20 and you say, I'm either leaving this casino when I go bankrupt or when I win £100, and you play a sequence of fair games when you win £1 or you lose £1, on average, it would take you as much as 1,600 of these games before you either go bankrupt or you win. And I mean, you might say, well, yeah, it's pretty difficult to get from 20 to 100. But remember that you can also go bankrupt. So you could also just lose all of your money as well. So I think this is quite a big number, all things considered, but that's the maths. Anyways, guys, I hope you enjoyed this video. There'll be plenty more videos on simple random walks, stochastic processes, gambler's ruin, all that good stuff in the near future. But I'll see you in the next one. Cheers.
That's just another way to say that I'm the best math rapper in the game today. It might sound vain, but it's just how I feel. And baby, I'm just trying to keep it real. Keep it real. Keep it real. That's right, Gowan was in deep trouble with the law. He's threatened government officials countless times and had been arrested.